So welcome to the fourth lecture in software architecture. Today we'll be talking about drawing pictures, and drawing pictures, not just any pictures, but partly, maybe the beginning, but we'll focus on UML. So as a practical experience we'll see some examples as a practical instances of experience in using UML, and what could you use in UML. Maybe you will recognize some things, some things you might not recognize that much. To get an idea, what can you do in UML? Some of your projects might be related to this, but even if your project is not directly targeting this topic, you can benefit very much from this lecture, because almost always you will need to express somehow your architecture visually. So before we start, just let's check where we are a bit. So we had 2 lectures related to patterns. One introductory lecture with a bit of everything, almost there, and we are heading for the half of teaching. So once we go through this lean architecture and DCI, which is actually devoted to the great extent to use cases and their position in software architecture. You can always check what the lecture is about, apart from the later lectures, because where I did not provide this. By clicking at this A, you can show the abstract. It's too small to show it here like this, but on your computers or even phones, it should look just fine and readable. So it is a kind of a. You can, of course, look at slides from the previous year to get a glimpse of what the lecture is about, but this is a kind of a readable and comprehensible short description of what the lecture is about. So then we will go again to patterns, but of the patterns of organizing people at software development, and then some reuse, distributed software architecture, maintaining software architecture. Here we will again go in these 2 lectures through patterns to a large extent. And then we will have this invited lecture, container-oriented software architecture and its implications, by the Deputy General Manager and the Executive Director at Regional Card Processing Center. Maybe I should have put there Raiffeisenbank. So I'm very glad that Professor Rankovic accepted this invitation. So I think we'll have a very nice lecture. Unfortunately, he could not make an earlier date, but nevertheless, we'll have him by the end of November. Okay, so that's it. What else happened? I actually reorganized lectures accordingly, so we will end with aspect-oriented modularization, so I moved the lectures a bit. If I get some other opinions from your side, I might still reorganize the lectures, of course, or if I come to some idea, or if any other invited opportunity for an invited lecture occurs, I'll do this. What I wanted to mention is that the next lecture here, as I wrote you, I won't be able to be here for the full length of the lecture, so we'll make it shorter. because I'm participating in the Pattern Languages of Programs conference. So anyway, we'll have plenty of time, and later than in the last lecture, the discussion lecture, to get back to anything that could have been unclear. You submitted your project objectives. Is there anything related to the project that you would like to discuss? I'm asking this before the lecture because after the lecture there will probably not be much time for this, although I will try not to take all the time. It doesn't seem so. So, anything else you would like to talk about regarding this course? Any questions to the previous lectures or whatever? Okay, so let's then get into this lecture on expressing software architecture in UML. We'll start by this question. With this question, why are we drawing pictures of software? Oh, I forgot to mention that anything you would like to say, you may use Slovak, like ask in Slovak or comment in Slovak, no problem. And I can answer in Slovak. So if anything is unclear as I'm talking, or any kind of strange expression you hear or whatever, just ask me and I will explain it. Might be as well my mistake, so that I've used something in a strange way. So anyway, the goal is for us to understand each other. So the question is short. Why are we drawing pictures of software? So take a minute to think about this and try to think like interactively and actively. So please talk to your neighbor for a moment or two about this. Or if you have any questions regarding the question. It's quite a simple question. So there must be some reason. So what do you think is the most prominent reason? So look for the most prominent reason. So when you'd be kind of giving me the reasons, you could have a whole list of reasons, but try to think of the most prominent one. Easier to understand, make easier to understand. Okay, you can continue talking to each other. I'm already accepting your answers, but I thought it might be good to give it a minute or two to think. So. Not red. What else? So make things easier to understand. Is it just that, or anything else comes to your mind? So if this is the most prominent reason for all of you, then look into your list and tell me the second one. Doesn't have to be the most prominent one. So another, whatever, and then the next one. Yes? Imagination. Anything else? To get a prototype. Anything else? Documentation. Anything else? Do you imagine developing software alone, or do you imagine it developing within an organization, within a team? Do you ever need to talk to someone when you develop software? Mostly not. Why talk? Just program. Simple and clear. You need to communicate. Output communication to play somehow. I don't know, what did I spoil here? Communication and documentation. Yeah. Would anyone like to comment on this? Because it's
people not from IT can understand.
Regarding documentation and communication. To communicate, yes, exactly. Why would you provide them some pictures? In order to communicate your idea. And this is probably, these things are quite connected. Imagination, this is like to imagine. Probably, I don't know who said this. Yes, you probably thought like or kind of conveying your idea or providing a picture of your idea on one side, but maybe you meant something else also?
When we create the software, we want to show somebody what we are trying to create.
We want to show somebody that, then it's communication. Yes, when we want to show somebody what are we creating. We know what are we creating, but we want to show this. But do we know what are we creating? Do we know that? Not always. Yes, sometimes we need to think, and how to think. I'm always urging you to talk to each other in order to foster the thinking process, in order to think better. It's also known that when you draw some things or write some things, people are drawing mind maps. So these are actually more or less like textual things, but mostly our pictures, when we draw pictures, we also annotate them, and most of the pictures, especially diagrams, is actually text. So you need pictures in order to think of what are you going to do, to create the idea, to come to the idea, come to the solution of some problem or whatever. So actually, it's not just communicating things, but it is highly interrelated, because hardly you do this alone. So you need to communicate, so you draw something and talk to other people, and they talk to you over this and so on. Sometimes when we establish things, we need to document them, to file them, put them somewhere for reference purposes. So sometimes it's that we can explain everything in words, or we think that we can do this or that, but actually some things, the ideas are a bit, the language of ideas is a bit different, or our mind is different. It's not just the language that we speak. So we need pictures in order to document what we meant. Then we comment on these pictures and so on. So we need this for documentation purposes. But very important, a very interesting note is this one: to get a prototype. So it's a kind of a paper prototype, to say so. Yeah. So it's not a prototype that really works. So if we create a prototype, if we say prototype, we usually think of some simpler version of a program that we are developing, and we usually draw away those prototypes, although we might kind of develop further our actual system on top of them. But usually this is not a very good idea, because we will be repairing many things, and in the end probably nothing will be left of that prototype there. So if we think of prototyping, what kind of model comes to your mind as kind of very close to a software prototype, which is not actually a prototype in the actual sense, like it's not a program? What model out of those that you know, not necessarily connected to UML? We mentioned that use cases in the first lecture already. Use cases are highly interactive. They show how the system will behave, and all stakeholders can reason about it easily, because it's readable. You might say it's not a picture, it's text, but you also can draw a picture. So there are use case diagrams. So more on use cases in the next lecture, although they are a part of UML through use case diagrams, but those diagrams are not enough to make this prototype, if we speak about prototype. So we never said this in our discussion now, But think about this for a moment. So why do we draw pictures? What's the point of all of this? All that we mentioned is about somehow making clear the idea or making easier for us to discover the idea, which is not that apparent either from some text description or in the end, not even from code. So that's why we need this for documentation purposes. So why would we need it otherwise? So pictures of software architecture should reveal what looking at code does not. We get back to this picture of Eclipse Link system that I showed you previously. So you see how this helps a lot. Very much. Exactly from this perspective, when you cannot read anything there. And so sometimes pictures are very, very complex because we are dealing with complex things. And we can even zoom certain parts, but we will not we will study different parts of this picture one by one, and then we will come to the idea of what this is. Maybe we will be reading some text that actually guides us through this picture and so on. It might be tens of pages, the description, and especially if it's a description, or this is a class diagram. So if it's just each class described, then we'll have a lot of trouble getting the idea what is this about. And we also saw this picture, which is a kind of a summary of the previous picture. So from this, certainly we can, it's readable. There's there is not too many elements there. They are related somehow. Not everything is clear, but we are getting the big picture of what's going on in there. So to understand the things. So we need maybe the detailed pictures to get the idea of detailed relationships, but when developing things, sometimes we need to put quickly something like this first to understand how the system will be organized, how it will be where and the position of that system. So Eclipse Link is just this rectangle there. So object data conversion and persistence manager, and it has interaction with other systems. So we see the context of the system, which commonly you do not see from a class diagram. So this is something when we are with class diagrams. Let's have a look at another class diagram. This is a class diagram of a kind of toy example that I use in another course called software modeling. This is a model of an e-shop, a part of it. So one thing there that you can see is this order class and how this order is constructed from products, services, possibly even there is a customer related to it, then a clerk that actually manages the order. There can be a special order, so you can see it is derived. So you know probably you understand these symbols. This is a elementary UML. So this is aggregation, this is inheritance or generalization, specialization, formally, colloquially called inheritance. So actually, it's like almost like a programming language because you have here attributes, you have here operations. Still, there are some differences. For example, look at this. This is this item. You can make it bigger a bit. Item, and here another item. These are marks. Also, you have this multiplicity symbol, like meaning many instances. So, like domain may contain order, domain order. Domain is a package where this class is placed, but this is not important at the moment. So an order can contain many products. So that's why this star is there. Also, this star could be put here, but this is not important at this moment. Look at this note, small note at the end of the edge. What is it? This is an association role, or just role. It's a role that this class plays with respect to this one. So this class acts as an item to this class. This is one of the things, if you would put together these things, you would not really see clearly in code these relationships. You might observe this relationship, though, because there will be a list of classes, maybe called items, here, as an attribute. A list of products, not classes. A list of products in the order class. So you might figure that the product class plays this role with respect to the order class. But the picture makes it explicit like this. Often we use these identifiers that we invent to name the role. So this name should be comprehensible and actually express the meaning of the relationship. So sometimes we use this to name the attribute that will occur in the aggregating class, but sometimes we can repeat it. So then we need to select something else. Yeah. So it is not an error to have several classes playing the same role. So we have this class playing this role of the item, and this class playing the role of the item. How would you put this together? By using what? You have one class and the other class, and they are somehow related. An interface, okay, but in general, so one class like A, B, an interface would be then somewhere here, or it may be another class. So either you would put it like this, or it could be an interface and then connect it like this, both of them. Yeah, okay. So a supertype, a type that is above these two classes. But sometimes we do not want to do this. These classes might not be related sufficiently, but they are related semantically somehow because they are used in the same way. So we could use the interface, but sometimes this is not so simply. Still, we have this role here. So this concept of role seems like a toy, but it isn't. It's an essential thing in our thinking about software. Unfortunately, it did not get sufficient space in UML. Although there was an attempt. So if you read carefully what you're using when you're modeling, it's not UML, it's UML2. It means that there was UML1 before that. And for UML2, they engaged Trygve Renskaug, who you might know from Model View Controller. So this is the guy who discovered the Model View Controller pattern. And he was very much into promoting this idea in UML and establishing it on a different base. But we remained with class diagrams. Mostly class diagrams are like another programming language, so they force us like with access modifiers and everything. Neviem. Ja som nič nenastavoval, ale je možné... Počkajte. Môžete zavolať CVKS, alebo... Neviete. We need to make a small break, sorry. No skúste niečo, tak skúste vypnúť. Je to počuť teraz? Je. Ale teraz nevieme, či je to v poriadku tam. No.
Však ja sedím pri dverách, tak mi iba povedzte.
Hej, tak vyskúšame iné nejaké prepojenie, dobre. Okay, so we'll continue. Sorry for this interruption. We'll get back. So this concept of a role is very important in UML. Although it is not fully implemented as it was supposed to be, we'll see that it occurs elsewhere as well. So what else do we have here is, for example, if we look at this, maybe even this diagram, I don't know. Here we can see that we can see something like this. This relationship that order manager uses this interface, and this interface is realized by this product manager. It can be realized by several other classes as well, of course. So this is something that you can see somehow in your code, but not that clearly. So this is just straight away, so you can see that this realization is there and that this use relationship is there. Otherwise, you will need to look inside of your code and look for this. Also, just check one thing. You might see this part. So let me draw your attention to this part. This is just a note that this is an observer implementation. But actually, you can implement or show your design decisions in your diagrams like this. But of course, again, this is just a class diagram. You can show this in a bit different way. When we speak of observer, we can do this like shown here. I'm making this bigger not because of these attributes, but again because of these roles. Do you know about what is this element? Do you recognize this element? It looks like a use case, but it's not. Not that much UML that you know, isn't it? Anymore. This element is called collaboration. Collaboration means that there is some interaction between some other elements that work together in order to provide some result. We are not very much interested always in some results, like so to have some box and some input, so something goes in and something goes out, and then another box, actually it's in then for this box and out, and so on. We're not always interested necessarily in the results, in algorithms, but how software is organized, how it is modularized, because we will need to work with it, to maintain it. It's a kind of a machine that has kind of its small parts that need to fit together. And we are connecting these machines like that, not just by wires, like in and out. We need to fit, like if we have some, I don't know, it's not a perfect picture, but something like this, some things that are connected that need to work together, to roll together in order to to get the whole thing work like a car, like something like this. It's not that just you draw your car to get the gases out of the car. That's the final product. It's to get somewhere and something to use your car in some way, in a certain way, and there are different ways. So enjoying the ride and everything, for example. So this is what we talk about. So that's why we need to talk about the appropriate, to have an appropriate abstraction of a collaboration. And it's not a complete abstraction, because we see here two classes that participate in order to get something. And these are the classes, as I said, observe this observer, observe this role again, so association role, subject and observer. So these two classes play these two roles within the observer pattern, which provides the mechanism to interconnect the objects of these classes, actually not the classes themselves, to be more precise, to get that behavior. Otherwise, these classes are normally like normal classes that we have that have their own business to do. But we need to connect them, because this one needs to observe the state of this one. And this is how, and we do not want to bother with the details, because we all know what an observer is. Or we pretend that we know that what it is. Actually, we can look anywhere, like in any design pattern catalog, to check up what it exactly does. But for the communication purposes, if we adopt this as a part of our vocabulary, then we can understand each other at a higher level of abstraction. We don't need to get into a detailed description of how exactly this observer is implemented. I lost this diagram. I had it here somewhere. Or maybe it's even here. No, it's not. It's the other one. Okay, it's open somewhere here. Yeah, so, and to analyze again, oh yes, this is an observer, and eventually to annotate this. But we do not see the roles exactly here, clearly. There's another possibility to play with collaborations. So we can do something like this. So we have a general observer, which is an interplay of a subject and observer. And then we have a derived, specialized observer, which is an interplay of an order manager and ordering form, with only one R that should be there. Sorry for this. So subject and observer. Here we have objects. So this is an object and this is an object, and they're related somehow, linked. We do not specify exactly how. Up there, these are not objects. And these cannot be classes, because they are inside of the collaboration, of a collaboration. What's inside of a collaboration is an instance. So these are kind of active roles. We do not know what these roles are, actually. We do not care about this. We do not want to say this. So something will play a role the role of the subject. Something will be an observer, or some other classes will be or instances of some other classes will be observers. So this is something that is present in UML that can be used and can be used like this and can be like made into even more complex diagrams to express our design decisions. And then we work with patterns explicitly. So there is some way to work with patterns explicitly in UML, although this is not something that you will see very often or at all, maybe in practice. Something to think of for your projects. Speaking of roles, we have a concept of role binding in UML. So once there is a role, you can bind something there like this. Again, this is something that you actually normally use in programming languages like Java or C++ or even C#, or it's generics or templates. So this is a template class. So you have a generic list class. So just observe that it's actually called list. And what do you keep in your list? Well, just about anything. Anything can be kept there. I just provide the functionality around it. And for the time being, it's only add item. I could have added some other operations because it's not a very useful list if you just add the items there. But in order to use this list, you need to specialize it. So you put a class that will play this role that is expected here. So this role is this generic type T. Not inheritance again. So this is something that you can use as well. And actually, maybe I will change the intended order a bit. We'll get back to this in a minute. But as we are with this binding idea, binding of roles, as we play with this, we'll jump right away into advanced package diagrams. I got back to some to remind you of some simpler uses of packages, but let's look at this picture. Is this UML at all? Oh yes, it is. There's this reference there. This is UML. This is valid UML. Although you might not get this completely right in your diagram. Not completely valid because this line should be dashed, but this is how I took it from the specification. This is a kind of realization relationship. So whenever you have a thing that looks like this, it's always a realization. So something realizes something. So it can be further specialized by providing a stereotype. A stereotype might be just that you invent a keyword a new keyword that you will be using. And you do not have to provide anything around it, but you give it some semantics on your own. So your interpretation is important. For this, for the bind relationship, there is some background to this within the UML meta model, of course, because otherwise you would not be capable of expressing this binding. But it's not important for us to directly go into the UML meta model in order to use this. So the interpretation is like this. You have a package of some generic system, and the system is generic, or a generic part of the system is indicated here by this dashed rectangle. Here are your template parameters like this. So it's a package template like class template. You cannot draw this properly in enterprise architect yet. At least I haven't checked, I must admit, the newest version, the latest version. But it wasn't possible. So the tools are do not, on one hand, they do not support everything that is specified within UML, or they implement it in different ways, or they add some things that are not in UML, or impose some restrictions that are not in UML. All kinds of weird things like this in tools. And all kinds of inconsistencies in UML specification, in the UML specification also, to admit so. So you have this template parameters like this. So you can look here. Here's resource kind here. Not really, it should have been in one line, but like this is not two words, it's one word. System is here. And this is a resource allocation. So you can imagine that you could have developed a generic resource allocation system or subsystem. And you can use it for allocating resources of just any kind. So you put this into work by binding car specification and car rental system to the appropriate elements in order to manage car rental things, because that's resource allocation in its own right. So this is a very interesting thing. So you can specialize your packages. There could be templates for this. So you can imagine generic models. You might not be able to implement this exactly like this without some language extensions or some management system put above, or some framework on top of your programming language, of course. But even though, to talk about ideas, I think this is something to consider. Looking at this, you see that these are not just like toy examples. These are not just like clouds connected by some weird lines and different colors there, and a happy user smiling and waving their hands and such things. This is not anything like that. This is quite a precise thing that we can reason about, like mathematical pictures, graphs, so a serious thing. This is just another example of a generic class, so it's in the specification, so it's not very important. This is also from the UML specification, but the thing is that these arrows are just simply wrong, and this is an issue. I think it was not addressed yet. So again, I must admit I did not check whether there is a kind of a new version that corrects these mistakes. These arrows are simply not a part of UML, and it's not like this that we use these dollar signs to mark things. Maybe we could, I'm not sure, but I think it's not like this in UML. So it's simply given by the names, like here, which are introduced here. So still this is a dashed rectangle. And what is interesting here, we have this training admin system, which actually makes use of this resource allocation system 2 times. So 2 different bindings. So once it puts the things for like instructors and qualifications, and the other side speaks about facilities and facility specification. And the same system connects these things. So when you put when you make these things double, but you do not make double this system class, all around it will be like one side and repeated on the other side. So if you would merge these things together, you would get quite a complex picture. You could do this. And you might ask, why the hell are we bothering with this? That we can draw simply this big picture with all the elements that we need. Is there a problem? Dobre. So, pokojne, okay. Plne te ignorujem. The thing is, if you recall that picture diagram of Eclipse link, you know what I'm talking about. So how many elements would be there? And we will lose our track there. So the thing is that by seeing this, we actually see our design decisions. Okay. So we see our design decisions, and if we need to generate the whole diagram, we can do this. But usually we do not do these things, do not do that. Like we would do this for maybe in implementation if we would not be able to implement this in a generic way like this. Then we will need to put everything on the table and repeat the classes and everything. But we keep track of our design decisions like this in a coherent way. This is also an open issue, like with this diagram. So in the previous version of the UML specification, it's like this, it's correct. And it's even this dashed line here, like this. And then it's not correct suddenly in this newer version. But that's a detail. This composition of packages is again related to the idea of roles, and this is probably what Trygve Renskaug wanted to have out of UML, to make pictures like this. Well, probably looking at this picture, you might say to yourself, well, I understand now why he was not allowed to do this. This is not UML. This is a notation that predates actually UML. This is the year when it was roughly published, but it was invented before. And Trygve Renskaug actually used it in practice to reason about the systems that he developed and his team and the colleagues developed. So this is an example of how this thing could, what is it about? It's about composing generic solutions like this, so producer, item, consumer. This is a generic way of expressing how you manage a lifetime, a life cycle of an item. So it's being produced and then consumed and so on. These are interfaces, these strange circles. So I'm not going to explain this notation anyway. I don't want to bother you with this. But so this is one thing, one generic thing, and the other generic thing is item-part relationship. And these two designs are actually quite generic and can be reused many times in many situations. And here is where they are applied to job offers, because they are also produced and consumed or used and so on. And some prerequisites might be a part of a job offer and so on. So this is this relationship. So the idea is for the pictures to allow us to think clearly, to draw what we need, to express our ideas in a generic way, and then reuse them. UML does not do that good job at this. There were attempts to put it towards this direction, but it's not finished yet. I hope that we will get back to this. So this is something. This is related even to aspect-oriented software modularization. We will talk about aspect-oriented modularization in the end of this course, as the current schedule is set. Not yet. So we'll get back to this, but let me show a few more things. Remaining with the concept of roles, but overall. But let's get back a bit to packages. Just for a moment. Simpler representation of packages. I think I've mentioned this as well. So you can use packages to represent how your system is modularized. When you think of packages in terms of Java or whatever programming language, it's always that packages are actually sets of classes. So they contain classes and they're not necessarily something that you can take and consider to be a component or a functioning part of a system. You think of packages as sets of related classes. But sometimes packages are compiled into working libraries that you can link to your program in some languages, or you can use them. It's like they are like frameworks, and you can organize them into sub-packages and sub-packages into further sub-packages. So that's one thing to think of packages. The other way of thinking about packages is when we put them together, like we want to provide a big picture of the system. So it's like this, that we represent the modules of the system as packages. Just draw them like this with no classes inside, and maybe we don't have an idea yet of what classes are there. For some, we do, because these are third-party components, and we think of these packages as components. So this is something that you might come across even today, but this is an earlier version of using and interpreting packages to represent subsystems or active components. For this purpose, UML provides what else but a component diagram now. So it was not always like that, but some idea of components. And actually, in earlier versions of UML, components were perceived more like objects. But then they got the flavor of class-like constructs. So these are like structural elements of the definition of the system, not active instances. You can instantiate components and then talk about their interaction. But this is a kind of how the system is established, and mostly we connect the components, just name them and connect which one is connected to which one. Maybe we make more precise these connections by declaring that one component uses another component. And there might be interfaces involved, but it might be a simple picture like this. We might, however, also go inside of some components and express what do they contain. And for packages, you would just maybe draw the classes that they contain. But for components, you might not go directly into classes, but you might represent the interaction or their inside as an interaction of roles. So here we have this order manager, which needs to manage orders, and we see that there is some order setup, order archiving, order content management. What are these elements? We might not know yet because we are just developing this idea. And we say, please do not force us to express our ideas exactly as classes, and with all the attributes, all the operations, and everything. It will be a mess, and we will not manage to convey our idea clearly, our essential idea. So that's why we use these elements, which can be implemented as classes, as interfaces, or whatever, then, and maybe actually decomposed into several classes. And we have this small rectangle at the border of a component, which is called a port. And these things inside are called parts. Parts of the component. What is a part? Well, some part. We do not specify that. And this port, what is this? Exactly. I don't know. We do not want to say what this port is exactly. Maybe it will vanish in the implementation. There will be no port to a component. Maybe it will be implemented as a class, because like maybe it will vanish and then this order setup will take the role of this element here and implement this ordering interface. And we use this ordering interface here, or interfaces here, like in a more like freestyle, not specifying exactly what methods do they prescribe. Sometimes we do this, like what operations do they prescribe? What's the contract? Simply by, we imagine this simply by naming them in a right way that expresses what we want to express. And again, on the other side, we have this this use of this interface also from this port. Order placement uses this interface. So we can have these interfaces. I think maybe that I have an example here exactly. If not here, then I have another version. Components like this. So this is if we want to be more precise with what uses what, and this might be the one with exactly with this interface. No inside of components is shown. No internals of components is shown. And the relationship between, but the relationship between order manager and order placement is depicted via this interface. No parts, no ports. So you can use interfaces without ports. So very different levels of abstraction that you can use with component diagrams. And if we get back here to this component diagram, and we spot here, and even in the same diagram you can combine these things, although when you start elaborating one component, usually you elaborate to some extent all the components in your component diagram. But sometimes like these things are clear and security kind of, I don't know, we've put it here, but what does it mean? Somebody might ask. And you might add some things there inside or in the outside of this component, some ports, but still it might not be clear how do these components interact. What would you use in order to express this? How do your components interact? How about this? What is this? Let's make some space, some more space. A sequence diagram. I heard someone said, or I will just pretend that I heard that. So a sequence diagram. So here we have instances of components interacting. And this is where we come to the difference between components and packages, because you cannot have an instance of a package formally. So packages are actually not intended. So wherever you see by Bushman and colleagues in their pattern-oriented software architecture, they're make heavy use of package diagrams to express components actually. So it's actually not correct, not a correct UML. but it's their notation. They can say, okay, this is what we use, and this is how we interpret this. But there was a lot of effort in UML to kind of develop a commonly understandable notation, and then someone says, okay, but I will use this like that, and that's not my business. Okay, you can do that, but you're making your pictures not readily understandable by others. Probably much of the UML that I showed to you is not readily understandable to you, even though you used the UML to some extent, or maybe even a lot, but you did not come across about these things. But these things are documented and interpreted like this, and if we are to get used to something, then it's better to get used to something that has an underlying meta model and use it properly. If it's impossible, okay, but for any other purposes, just think of it. And this sequence diagram is a quite simple sequence diagram that shows how security is put in charge, or is in charge, what does it handle, and what does it mean, what does this component mean within the system. This sequence diagram is not a complex sequence diagram with all those combined fragments or making references to other diagrams that simply clutter the diagram and make it completely unreadable. This is a very simple diagram that shows one possible interaction. And this was the intended purpose from the beginning of sequence diagrams. Then they were spoiled by the idea, oh, this is a notation that can be used to depict the whole interaction in all possible cases, under all conditions and so on, to actually graphically express operations, method bodies. You can do that, but it's like too much detail. And in pictures, we need to express often like particular situations. We cannot come at once with a generic solution. So we depict different scenarios of how components interact. By the way, I will provide this model to you, and the exact list of the diagrams. It's a kind of it's not a big model, that big model, but to make your life easier, I will provide exact references how to get to these diagrams in this model. We can express this also like this sequence diagram, by the way. We can express it like this. What is this? What kind of diagram is this? What's the name of this diagram? This one is called communication diagram. Communication diagram can be generated in Enterprise Architect and some other tools as well from the sequence diagram, and vice versa. Just another way to depict things, how the communication runs across these components. And further, one more thing are these messages here. Sometimes you need to be very precise and to say what the message is, and usually you have no other option but to say it's an operation call. But in general, messages can be just anything. They need not be bound to operation calls. In that software modeling course that I mentioned, that I use this example model, we force students to have for each message that to have the corresponding operation in the back. And actually you can see like this that you can set what you need here in the properties. So here I have this. This is a message, but if I would add a method or an operation to my component, I would be able to select the exact method here or operation. Operation is a UML word for a method in object-oriented programming, or what we call method. So check order is just a string of letters. I can write anything there, and it will be valid. But if I want to be more precise, I can start adding operations. And by that, I can start working actively with the model, and I can start like getting it to a higher level of precision with more details, getting it ready for the implementation. So any questions so far? Any really obscure element or whatever you would like to be explained? Doesn't seem so. What's this one? This is an eShop server, and this is a client station. More like hardware components. And we see component instances running on these computation nodes of our complex distributed system. We see how they are deployed. This is a deployment diagram. It was a very popular kind of a diagram in UML, and still it's being used. Usually you see deployment diagrams drawn as kind of like free pictures, like free diagrams with cloud that represents a network and such things, and users and so. I could have added a user, so there's a symbol for a human actor in UML anyway. But actually what's interesting here is that we can see how things are like distributed. And these computation nodes need not represent hardware components. These might be systems where our components are put to run upon which our components actually run. And here you can see, deployment diagrams have been like part of UML, maybe from the right from the beginning. And you can see why components, not exactly maybe, but the idea was tightly connected to the idea of a component as an active part, as an instance. So that was at the time when the components were perceived like that. Now we perceive components as also as classifiers. These are kind of sister elements to classes. If we get back to packages, I forgot about one fancy thing with packages. We were close to this, but this is a bit different. Let me just put it right. We could have an idea of implementing some fancy ordering with a special order manager that implements this fancy order method. And this normal order manager implements all the rest. So in order to make this work like this, we need to compose these two things. So this fancy order manager is not really, does not stand on its own. It just adds something. Do you recognize this from some programming languages? Not really? And it's not inheritance that we use. So we compose these two things. We merge them. This relationship, to me, seems like not exactly right. So this means that actually this ordering package merges the contents of this package. You cannot put this merge relationship directly between classes, but you can do this between packages. And this one swallows, so this one on the left side swallows this one and interconnects whatever is there in this order manager, adds these things into this order manager. I don't really remember what happens if you have the same elements. I'm not sure. Maybe you can specify this somehow aside. But the idea is to compose whatever is there in this order manager. Anyway, it's not working code. Yeah? So it's just a model. We can represent anything we want. But by this, we represent this design decision that we have this basic order manager, and then we have some additions to it. We will get back to these kind of things in the aspect-oriented modularization lecture, because it's based on such relationships and compositions, but it's kind of more like these relationships goes the opposite way. By this, actually, you say that this ordering package knows about this fancy ordering. So the relationship is this basic implementation knows about what is to be added. While in aspect-oriented software development, aspect-oriented programming, it goes the opposite way. So this kind of aspect knows about the whole, and the whole does not know about the aspect. Anyway, a composite implementation is derived from this that contains all the things and manages all the things that it should. So this is this merge relationship, which is heavily used in the UML specification. So if you open UML meta model, you will find it's heavily used there. However, we rarely see it in application models, but it can be used to express the idea. So implement this exactly like this. But some programming languages do support these things. This is not inheritance, not exactly aggregation. Have you heard of traits? Traits. Small classes that can be added, composed with other classes, just to be composed with other classes. Why would you need something like this? Let's put everything together in one big class. Yeah. So it doesn't work that way. We need to get things, to make things reusable, not for the sake of the community, of the world, of for other people, but for the sake of our organization or for our own sake, because we will be like restructuring our code indefinitely, and with any with whatever comes, any other requirement that comes on the table, we will be re-implementing things, reorganizing them, and so on. So we need to decouple things and to get them reasonably composed. So even if we cannot implement exactly these merge relationships in our code, it's nice to reason in terms of this relationship, to pretend that we have this. What else? These are the things that I showed to you. No other things, actually. You can check up this site. I find it pretty good, and it even warns about some inconsistencies in the UML specification. I don't know whether the author tried to publish this as a book or something like that, but some good things do not all good things necessarily finish as books, and not all books are necessarily good. So this is kind of very interesting and good reference site for UML. So you can see various uses of package diagrams there also. And just to recap this, UML expresses structure with varying detailedness and composition mechanisms. That's one thing. The other thing, we saw that sequence diagrams could be used for essential interactions. So you might not have expected this. You might have expected, when we talk about architecture, it sounds like a timeless concept, and it is. As something stable, something structural, the basis for everything, not moving at all, but actually we need to understand the dynamics, how this architecture is going to be used. And for this we use sequence diagrams or communication diagrams, maybe activity diagrams, or state machines. I did not show anything, any examples of this, but you can imagine using all these things to represent whatever you find crucial for your architecture, key things. Do not draw many pictures, draw the essential ones. Unless you are forced to document everything. If you are forced to document everything, put forward the most important pictures, because somebody might really be reading the documentation. It might come as a surprise, but sometimes the documentation is being read. Not very often, though. This is a thing that we will talk about in the next lecture. So I'll just leave this question as a kind of an initial question or an impulse for the next lecture. Are use cases a part of software architecture? And we came up to the idea of having a prototype in form of use cases. But can we push forward this idea to something more complex, or going directly from this into implementation? But I would like just to remind you that of this dynamics, that with behavior, which is important for architecture as much as the structure is, expressing essential behavior in UML can help understand how the architecture actually works. So this is actually the end of this lecture. It's time for your questions, final questions. It's always time for your questions, but now is the last minute for your questions. Comments, opinions, whatever. Say something. Talk to me. If you don't want to talk publicly, there will be, of course, a few minutes to talk to me privately afterwards. Okay, thank you for your attention. See you next time. It will be a shorter lecture, about 1 hour. Oh yes, and for all of you who have your master's thesis or are starting with your master's thesis, this výskum inteligentných softwarových systémov pokračuje teraz o 4:00.